Hello again. Yes, I'm back. I'm back with some more videos, okay? Sorry I've been away, but things have happened. Anyway, I want to talk to you about exponential graphs and logarithms, okay? Because I really love this topic, and I've just noticed I've not done any videos on those so far, so well done for tuning in. Hopefully you'll pick up something, okay? Here's a typical exponential graph, y equals 2 to the x. Now let's talk about why it looks like that. Here's a simple table of values, okay? So what I've got is some x values that I'm going to substitute in, 0, 1, 2, 3, 4, 5, and using this base number as 2, I'm going to do 2 to the power of each of these values. Start with 2 to the power of 0, which is 1, of course. 2 to the power of 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4 is 16, 2 to the 5 is 32, okay? Now what you notice is that as the x values increase, the y values increase, wait for it, exponentially. Yes, that's the reason why these are called exponential graphs. As the x values increase, the y values increase at a much faster rate. That's what we mean by an exponential increase. Okay, so from here, the y-intercept, you can see the graph is actually curving upwards, and the gradient, that's an important term in A-level maths, the gradient is getting much, much higher. It's increasing quite quickly. Okay, hence the curve is sloping upwards like this. Now what's happening to the left of the y-axis? Well, what I'm going to do is I'm going to substitute in some negative values and see what happens. You ought to be aware that 2 to the power of, let's try that again, pen mode. 2 to the power of -1 is the same as 1 over 2. Okay, using your rules of indices there. And 2 to the power of -2 is 1 over 4. 2 to the power of -3, 1 over 8, because it's 1 over 2 squared, 1 over 2 cubed. So for these negative values, notice you get the same numbers appearing, but they're reciprocals, okay? So 1/2, 1 over 4, 1 over 8, 1 over 16. So as the x values get larger but negative, if you can put your mind around that one, okay? Larger but negative, these values are getting smaller, smaller, smaller. One of the questions is, can these y values ever be 0? The answer is no. Because if you rewrite this as 1 over a number, doesn't matter what number you choose, 1 divided by, choose any number, either really small or really large, you'll never get 0. You cannot divide 1 by a number in order to get 0. Okay? You could divide an extremely large number, like a million or a billion or a trillion, it won't actually be 0, will it? It'll be very, very close. But that's what's happening here, okay? As the x values get larger but negative, the y values are getting smaller and smaller, but they'll never be 0. Okay? And that's why the graph tends towards this horizontal axis. That's why it's called an asymptote. If you've not heard that word before, write it down. It's a really important word in A-level mathematics. An asymptote is a line that a curve of a function will tend towards, never touch or cross, but it will tend towards it, okay, as one of the extreme values normally. So that's the graph of y equals 2 to the power of x. Now what I'm going to do is I'm going to show you this. Here's my bit of advertisement for Desmos. Thank you, Desmos. I do love what you do, okay? These make my presentation so much easier. And for Desmos, I'm going to put in 2 to the power of x, 3 to the power of x, and a couple more, okay? So this is the graph of 2 to the x. What I've done is I've just plotted it so that these are accurate, but I've just taken off the scales and the labels and the grid. So this is the graph of 2 to the x. What do you think happens to the next one? 3 to the power of x. Notice what happens? Well, there's 2 stages. Basically, the graph is steeper on this side, isn't it? Okay, notice, because instead of doing 2 squared, 2 cubed, 2 to the 4, you're doing 3 squared, 3 cubed. So let's just take a general point, okay? Oh, I should ought to be in pen mode again, really. Suppose that is x coordinate of 2. 2 squared is 4. 3 squared is 9, much larger, okay? Because these are powers of 3, they go up much faster, don't they? Powers of 2, 2, 4, 8, 16. Powers of 3, 3, 9, 27, 81, and so on. They go up much faster now. So it's actually steeper. Notice the y-intercept is the same because 3 to the power of 0 is still 1. Okay? Then underneath, can you see what happens underneath the graph? The blue part of the graph, that is 3 to the power of x, is actually smaller because, let me just go back to this screen here. If I place these values with their reciprocals, can you see what's happening? Instead, if I have 3, 9, 27, 81, I'll have 1 over 3, 1 over 9, 1 over 27, 1 over 81. They're actually much smaller, aren't they? And so the graph is actually going to be underneath the bar. There's a crossover bit here. Now, can you work out what the next one is going to be? That's 10 to the power of x. Here it is. There we go. And it's steeper again, isn't it? Because these are now powers of 10, 100, 1,000. Wow, went up really quickly, didn't it? Okay. Hence why we call these exponential. Okay. The word exponential means there's a really big change of y values compared to the relatively small change in x values. Okay. And same with these. If I take reciprocals of 10, 100, 1,000, I get 1/10, 100th, 1,000th. And so the graph is actually getting even closer to the x-axis, even closer to 0. Okay. Now, to put one more in there, y equals e to the power of x. You may not have heard of the number e before. If you have, well done you. Okay, but e is an irrational constant, a little bit like pi, but even better. I'm sorry if that upsets some of you, because there's a bit of an argument as to what mathematicians prefer, whether it's pi or e. Personally, I prefer e. It's got a lot more glamour around it, and I can start talking about Leonhard Euler, who's my all-time favourite mathematician. If I can go back in time and meet any one person, it would be Leonhard Euler, okay, because it's just fantastic. Anyway, more on that. E to the x can be done because e is just a number, 2.71828, despite what I just said, it is actually an irrational constant. The 1828 just makes the first few bits easy to remember, okay? But it's going to slot in between the 3 to the x and the 10 to x, isn't it? Okay, so it's the the 3 to the x and the 2 to the x, because it's 2.71828. So it's around about there. Anyway, you don't really need to know about e to the x until year 13, but you've got it. Okay, I've actually done it for you. Okay. Now then, I'm going to show you something else. What happens if we just take any number, a, where a is, well, obviously not 1. Okay, 1 to the power of x is just going to be 1 all the time, and not 0. Okay, because 0 to the power. Basically, any other number. Okay, let's just keep it positive for the time being. Okay, just to be absolutely simple. So any positive value, just not 1. The general graph of a to the x looks like this. Okay, it's an easy curve to remember because this is what we call an exponential curve because it increases exponentially. We use that term. The y-intercept is always 1, okay, because a to the power of 0 will be 1, except for when a is 0, of course. And of course, we don't have this curve when we have 1 to the power of x, do we? Yes, this is your general a to the x exponential graph. Okay, that? Well, I hope so. If not, just watch the video again. That's the beauty of these. If there's anything you didn't get, just watch again, okay? I just want to talk to you about these graphs, okay? This is a downward sloping curve, a reverse exponential curve graph if you want. This is when you have a to the power of negative x. Now, the reason it looks like this is because you can actually write it as 1 over a to the x. Don't be confused about the negative values, okay? The negative powers there. Notice in this graph there's nothing underneath the x-axis. Reason is you cannot do 2 to the power of a number and get a negative answer, or 3 to the power of a number and get a negative answer. You cannot input any value of x into this in order to get a negative number. The negative power simply means the reciprocal of a to the x, which is 1 over a to the x, like that, okay? Now, do you remember your transformations of graphs? I really hope so. This is explaining why the graph is actually the mirror image, the reflection through the line x equals 0, the y-axis, okay? So if you remember your transformations, we're looking at this, f of negative x, okay? F of negative x. The transformation f of negative x on the graph, f of x, means you reflect the whole graph through the y-axis. So what that means is, if we replace 2 to the power of x with negative x, you reflect the 2 to the x graph through the y-axis, and you get the graph of 2 to the negative x. Okay, so in terms of transformations, that's why the graph looks like this. Okay, oops, pretend you didn't see that. I just went the wrong way. So here's a to the x and a to the negative x. Okay, the reason mathematically it's doing this, apart from the reflection bit, is because the larger x gets, the smaller y gets. I can write down this. Okay, as x gets larger, we tend to say as x tends towards infinity, okay, x gets very, very, very large, then y gets much, much smaller because you're doing 1 divided by a very large number. So what we're saying is as x gets much larger, y gets much smaller. So that's why it's tend towards the x-axis on this side. Conversely, as x gets larger but negative, you put in negative numbers, the negatives cancel, don't they? If you put in negative 2, it now becomes a to the power of positive 2. If you put in negative 3, it now becomes a to the power of positive 3. And so the larger the values used but negative, negative 1, negative 2, negative 3, it means you've got the reverse exponential effect. Okay, and that's pretty much what exponential graphs are all about. Okay. Okay, so now we're going to talk about what we mean by a logarithmic graph. This won't take long. Now, a logarithm is the inverse of an exponential. Okay, let's start off with that. I've got another video which talks about logarithms in a different way, but I always like to think of a logarithm as the inverse operation of an exponential. Here's an example. I've got a graph of y equals 2 to the power of x, and I want to sketch the inverse function. You ought to have done some work on inverse functions, maybe at GCSE or some other mathematical course that you've been on, but you ought to have some awareness of inverse functions. An inverse is the exact opposite operation. Now, strictly speaking, for an inverse to exist, the function must be one-to-one. So we're fine here because that is a one-to-one function. If you want to know what one-to-one functions are about, look it up or have a look at one of my videos. I hope I've got one there somewhere. If I haven't, I apologise, and I'll get on the case as soon as I can. Okay, but this is a graph of y equals 2 to the x, and I want to find the inverse of that one-to-one function. The method graphically is to reflect it in the line y equals x. And that line looks something like this. So I put it as a dashed line because that's not actually an equation of a curve on this set of axes. Okay, I want to reflect it through that line. When I reflect it, I get this curve there. Rather simple, isn't it? So the exponential curve just gets reflected through the line y equals x onto this curve there. And that is it. That's what we call a logarithmic graph. And let me just show you a little bit better what it looks like. So here's one I did earlier, but using Desmos, of course, and I just labelled it up. So here's the general function, y equals a to the power of x. Do remember the y-intercept is always going to be 0, 1. When we reflect this whole graph through the line y equals x, we get a logarithmic graph, okay? Notice that the y-intercept becomes the x-intercept, 1, 0. That's because in the reflection process, all the y values and x values, they swap around. Remember, the domain and range, they get swapped around when you're finding an inverse function. Now, the inverse function is a logarithm, but we've got to pay attention to what base we are using. That's why earlier at the start of the video, I referred to this as a base. We had base 2 for 2 to the x, base 3 for 3 to the x. Now, the base of that is a, which means the logarithm base we need to use is also a. Had it been the case, we were dealing with y equals, let's just choose a different number completely. If we were dealing with y equals 7 to the x, yes, of course, the graph would look steeper than this, look something like that. The actual logarithmic graph would be slightly different, wouldn't it? Okay, so it's not just one logarithm graph, there's a lot of log graphs depending on what base we're actually using. That's going to look slightly different. And the inverse of that would be log base 7 of x. And that's why we do lots of different bases. Base 10 and base e are just the most convenient when we happen to want to solve an actual problem. Okay. Now, I did show you this earlier by accident, so I wanted to put it up again just so I can explain what it's all about. Here's just two comparative graphs. The graph of 2 to the power of x and the graph of e to the power of x. Remember, e is about 2.7, 1828, 1828, etc. An irrational constant. Okay. Well, the inverse of e to the x will be log base e of x. Okay. Now that's sometimes written like this, log base e of x. But since log base e of x is what we call the natural logarithmic base, maybe you have to look at some year 13 videos to understand what that means. Because it stands for the natural logarithmic base, we abbreviate it to lnx. Stands for log naturalis. Logarithm naturalis, Latin for the natural logarithm. Okay, thanks to William, can't remember his name now. An American mathematician. Irving Stringham, I think his name was. Okay, maybe it was a bad moment to suddenly think of his name. I didn't. Yeah. Anyway, one of his contributions to mathematics was to come up with the notation lnx. But we always say it as a natural logarithm when we're writing it down. So that's the natural logarithmic graph. So that's your basic introduction to logarithms, okay? They are the inverse of an exponential, and the graphs always look like this, okay? We tend in nature to talk about an exponential increase or a logarithmic increase, okay? If the function is most applicable to that. Well, I'm hoping you got something out of this video, okay? I'm hoping that you really, really enjoyed it, okay? I'm going for one finally. William, oh my God, I had to eat my head. William something Ingham, okay? I'm going to pause the video, research it, and then put it up there because I've just not done him any justice, have I, okay? Hold on, I'll be 2 seconds and I'll be right back. There, I told you it'd be a couple of seconds, okay? There it is. I've not mentioned his name for about a year or something like that. So I remembered William, of course. I knew William Irving Streamer. Okay, so American mathematician, 1847 to 1909, first introduced the notation for the natural logarithm ln. Okay, where e, of course, and I've got the number written for you. Okay, and this is what the graph actually looks like. Okay. Now, while I'm on the subject, okay, of mentioning people, you should be aware, or you may be aware, that John Napier, the inventor of logarithms, Scottish, okay. Now, this mathematician, don't hear of many Belgians, do you, okay, but Grégoire de Saint-Vincent, he actually discovered the natural logarithm himself. So although it took a long time for us to use the notation lnx for the natural logarithm, it was actually discovered way back in the 16th, 17th century, as you can see, okay. And the first use of this term, log naturalis, remember that is Latin, so it was a long time ago, was in the 1600s, okay, by this German mathematician, Nicolaus Mercator, okay. Anyway, just a brief bit of history, basically because I started talking about it. Right, there we go, okay, I'm just going to leave the screen so you can get a snapshot if you wish. Done? Yes. It's good to be back. It feels like I've been back a long time. It's good to be back. I'll see you again.